Have you ever stared into the night sky and felt like something was watching you back? Not with eyes. Not with malice. But with a cold, endless silence that doesn't blink. It just waits. Behind the veil of stars, somewhere between the light that reaches us and the darkness that devours it, lies the most profound mystery in the known universe: black holes. They're not just cosmic monsters. They're portals into physics we barely comprehend. Secrets we haven't unlocked. And perhaps, gateways to other realities? Before we fall too deep, let's zoom out. Let's remember who we are: tiny beings living on a fragile blue marble, orbiting an average star in a galaxy among billions. And yet, we dare to ask questions the universe itself doesn't always answer. We send telescopes to stare into the void. We launch probes into emptiness. We listen for whispers across light years of silence. And sometimes, the universe answers back, not with words, but with puzzles. But before we continue, subscribe to the channel and like the video. Black holes are among the most terrifying and fascinating riddles we've ever encountered. They are real. They exist. And yet they defy logic. You can't see them directly. You can't escape them once you're too close. And if you fall into one, physics, as we know it, breaks. But black holes are just one thread in the massive, tangled fabric of cosmic mysteries. Think about this: 95% of the universe is made of something we can't even see. Dark matter. Dark energy. They make up nearly all of reality, and we have only theories to explain them. It's like living in a mansion and only knowing one room. The rest. Completely dark. And time itself changes near a black hole. Did you know that? It's not science fiction. It's measurable. If you were to float just outside the event horizon of a black hole, a few minutes for you could be thousands of years for everyone else. Gravity, in its most extreme form, bends not just space, but time. And that's not an exaggeration. That's Einstein, confirmed by observations. But let's go even deeper. What if black holes aren't just cosmic garbage disposals? What if they're engines? What if they power galaxies, birth new stars, or even serve as bridges to other parts of the universe? Wormholes? Parallel universes? The math allows it. The observations hint at it. The questions haunt us. Now, let's slow down and ask, what is a black hole, really? At its core, a black hole is a region in space where gravity has become so intense that nothing, not even light, can escape. This isn't metaphor. It's reality. It starts with a star much more massive than our Sun. When that star dies, it explodes in a supernova, and its core collapses under its own gravity. If the mass is high enough, nothing can stop this collapse. The core gets denser, and denser, and denser, until it becomes a singularity, a point of infinite density, zero volume, and infinite gravity. Let's pause for a second. Infinite density. Think about what that means. All the mass of a star, compressed into a single point. Not a speck. A point. No space. No width. No depth. Just gravity. We don't really know what goes on in a singularity. Our physics breaks down. Even the math becomes unstable. It's where Einstein's general relativity collides head-on with quantum mechanics, and both scream in confusion. Surrounding that singularity is the event horizon, the boundary beyond which nothing returns. It's like the cosmic version of abandon all hope, ye who enter here. Once you cross it, escape is impossible. No rocket. No light. No information. You could shine the brightest flashlight, and its beam would just curve back in. Black holes don't just eat light. They cage it. But here's the kicker: black holes aren't rare. In fact, there's likely one at the center of every major galaxy, including our own Milky Way. And our galaxy, with its spiral arms of hundreds of billions of stars, is just one of over 2 trillion known galaxies in the observable universe. Each potentially with its own supermassive black hole at the center. Just imagine that for a moment. Trillions of galaxies. Each with hundreds of billions of stars. Each with a monstrous black hole in its heart. The universe is not empty. It is filled with things we do not understand, and the things we can't see might be the most important of all. Consider this. The first actual image of a black hole, taken in 2019 by the Event Horizon Telescope, changed everything. For decades, black holes were theoretical. Now, we've seen one, or rather, we've seen its shadow. A perfect ring of fire surrounding darkness. It was like staring at the eye of the cosmos itself. And it wasn't just a scientific achievement. It was a poetic one. Proof that even the invisible can be captured, if only you know how to look. But the deeper we stare into space, the more the universe resists explanation. Take Hawking radiation, for example. Stephen Hawking predicted that black holes slowly emit radiation over time, eventually evaporating completely. That means they aren't eternal. They die. But how do they release radiation if nothing can escape? That question leads to the infamous information paradox. If matter falls into a black hole, and the black hole evaporates, where does the information go? Quantum mechanics says information can't be destroyed. General relativity says black holes erase it. Who's right? No one knows, yet. And let's talk about spin. Black holes don't just sit still. They rotate. Fast. Some near the speed of light. That rotation twists the fabric of spacetime itself. Picture stirring honey with a spoon. The faster you spin, the more everything around it swirls. That's what rotating black holes do to space and time. Some theories suggest that if you could navigate this swirling vortex just right, you might avoid the singularity and come out the other side, perhaps in another part of the universe. Or another universe entirely. Sound like science fiction? It is. But it's also science possibility. And that's the most thrilling part. Now, let's move from the known into the suspected. There's a class of objects scientists have never seen, but believe must exist. They're called primordial black holes. These aren't born from dying stars. They may have formed just after the Big Bang, squeezed out of the raw, chaotic energy of the infant universe. If they exist, they could be the key to dark matter. They could explain gravitational waves. They could be everywhere, tiny black holes drifting silently through space, even through our own solar system, undetectable until one passes too close. But black holes aren't the only cosmic riddles out there. Why is the universe expanding faster than it should be? Why is there more gravity than visible matter accounts for? What is the true shape of the universe? What was before the Big Bang? Every answer we find in space only raises more questions. The more we look, the stranger it gets. We've found stars that shouldn't exist. Galaxies that formed too early. Radio signals from deep space that pulse in perfect rhythms. Some occur once. Some repeat. Are they natural? Are they signs? Are they errors in our instruments? We don't know. What we do know is that space doesn't care about our expectations. It doesn't fit into our boxes. It doesn't obey the limits of human imagination. It's bigger, weirder, older, and far more dangerous than we ever dreamed. And yet, it is beautiful. The beauty of the cosmos lies in its refusal to be fully understood. It's a puzzle without a box top. A riddle where the question changes as you answer it. A story that began long before us and will continue long after we're gone. So as we peer deeper into space, chasing signals, chasing shadows, chasing the edges of black holes, maybe the most profound truth we'll ever find is this. We are part of the mystery, too. Let's turn our gaze back toward the phenomenon that holds scientists and philosophers in equal parts or in terror, the singularity. We often say black holes break physics, but that phrase barely scratches the surface of the chaos they introduce to our understanding. Inside a black hole, beyond the event horizon, gravity no longer behaves the way it should. Time and space are not just distorted, they're inverted, swapped, twisted into something alien. It's as if the cosmos itself hits a glitch in its own source code. And what's more chilling is this: every law we hold dear, from Newton to Einstein, bows in defeat at the edge of a singularity. But what is the singularity? Is it truly a point of infinite density, or is it simply a placeholder for our ignorance, a mathematical artifact of a theory not yet complete? Many scientists believe it's the latter. General relativity predicts the singularity, but quantum mechanics, which governs the very small, rebels against it. The conflict between these two foundational pillars of physics is perhaps the greatest unsolved problem in science. Enter quantum gravity, a theory that doesn't exist yet, but one that must. A unifying theory that would explain gravity in the quantum realm. String theory, loop quantum gravity, holographic principles. These are attempts, glimpses, sketches of a deeper truth we haven't grasped. If we ever find the right theory, we may learn what lies at the heart of a black hole. Is it a tear in the fabric of reality? A doorway? A dimensionless point that contains everything? And then there's the tantalizing idea of information preservation. According to quantum theory, information, the specific details about a particle's position, momentum, and spin, can never be truly destroyed. But if something falls into a black hole and the black hole evaporates, where does that information go? If it's lost, it challenges the very foundations of quantum mechanics. But if it's preserved, how? Some propose that information is somehow encoded on the event horizon itself, like a cosmic hologram. This idea led to the holographic principle, the notion that all the information contained within a volume of space can be represented as a theory on the boundary of that space. It's a staggering idea. Our three-dimensional reality might actually be a projection from a two-dimensional surface. Like a movie projected on a screen, the universe could be a hologram, with black holes as the testing grounds of this cosmic illusion. Even Stephen Hawking revised his views on the matter late in life. He proposed that information might leak out of a black hole via quantum fluctuations, possibly encoded in subtle patterns in the Hawking radiation itself. If true, this would mean black holes don't destroy information. They scramble it, distort it, stretch it across time, but they don't annihilate it. Think of it like burning a book. The information isn't gone. The ashes, smoke, and heat contain traces of every letter. The challenge is reconstructing the novel from the debris. But theories are one thing. Evidence is another. And evidence in the realm of black holes is extraordinarily difficult to obtain. You can't poke one with a stick. You can't observe what happens inside. All we can do is study their effects. Gravitational waves from collisions, accretion disks glowing with X-rays, stars dancing around invisible points in space. In 2015, the LIGO experiment detected gravitational waves for the first time, ripples in the fabric of spacetime itself. These waves were born from the collision of two black holes over 1 billion light-years away. When those two titans merged, they released more energy in one moment than all the stars in the observable universe combined. And we felt it, on Earth. It was the faintest whisper, a contraction and expansion smaller than a proton, but it confirmed Einstein's wildest prediction. We had listened to the universe, and the universe had sung. These gravitational waves carry secrets. They tell us how black holes dance, merge, and die. They offer new ways to study the cosmos, not with light, but with vibrations. It's as if, for the first time, we're learning not just to see the universe, but to hear it. But what about what we don't hear? What about the silence? Consider Sagittarius A, the supermassive black hole at the center of our own Milky Way. It sits in quiet authority, weighing in at over 4 million times the mass of our Sun. We've tracked stars spiraling around it, accelerating to millions of miles per hour, whipped into elliptical orbits by a force that has no visible source. That invisible pull, that abyss, is our galaxy's anchor. And yet, it barely flickers. It's relatively dormant, not feasting on matter like other active galactic nuclei we've observed. Why? Is it sleeping? Is it in a phase we don't understand? Or is it something else entirely? There are even wilder ideas. Some suggest that black holes could be conscious. Not in the way we understand mind, but as entities that process information, evolve, and respond. Is this speculative? Certainly. But so was the idea of black holes a century ago. So was gravitational lensing. So was dark energy. Sometimes the universe laughs at our skepticism. And speaking of speculation, let's take a step into the truly exotic, white holes. These are theoretical opposites of black holes, regions of space that expel matter and energy, but cannot be entered. Some physicists propose that black holes and white holes are two sides of the same coin, connected through a wormhole. If true, A star collapsing in one universe might become a white hole in another, ejecting matter that looks, to observers there, like a Big Bang. Could our universe have been born from such an event? It sounds absurd. And yet, every Big Bang theory starts with a singularity, a point of infinite density. The same as in a black hole. The equations are hauntingly similar. It begs the question, are we living inside a black hole? What would that even mean? It would mean that our universe, everything we know, is the interior of a black hole born in a higher dimensional reality. The event horizon would be the boundary of our cosmos. Everything we observe, all the galaxies, all the light, all of time itself, could be the interior of one massive gravitational object in some larger meta-universe. This isn't just a philosophical musing. Some physicists have built models supporting the idea. It could resolve several paradoxes about cosmological inflation, entropy, and the apparent uniformity of the cosmic microwave background. If we are inside a black hole, we may never know it from the inside, but the clues could be written in the large-scale structure of spacetime itself. And as we drift through space, orbiting an average star, it's humbling to consider that we live in such a precarious and hidden reality. We build satellites, particle colliders, and space telescopes not just to understand the universe, but to understand our place within it. And yet, we're fragile. Our entire civilization exists in a narrow band of time, on a tiny crust of rock, shielded from oblivion by a thin film of atmosphere. A single gamma-ray burst from a distant supernova could sterilize our planet. A rogue black hole passing through the solar system could shred Earth's orbit. These aren't likely events, but they are possible. And so, we look to space not just with wonder, but with urgency. Space is a mirror. When we stare into it, we see ourselves, not as masters of nature, but as its students. Its children. Its echoes. Somewhere out there, between the galaxies, between the pulses of dying stars and the gravitational waves of colliding black holes, there is meaning. Or perhaps the meaning is in the mystery itself. To seek, to ask, to never stop wondering, that is the legacy of humanity in the face of the infinite. And so, we continue to explore, not just for answers, but for better questions. The story of our cosmic journey is as old as firelight storytelling and as new as quantum simulation. We are compelled to look up because, deep in our evolutionary DNA, we've always needed to understand what lies beyond the horizon. The night sky, speckled with stars, has been our map, our calendar, our myth, our mystery. And today, with tools of almost godlike precision, we gaze deeper than ever before, not just in distance, but in time. When we peer into the depths of the universe, we're also looking into the past. Light from distant galaxies takes billions of years to reach us. The farther we look, the younger the universe appears. And yet, even in its infancy, there are surprises. Galaxies forming earlier than models predict, supermassive black holes that shouldn't exist so soon after the Big Bang. These black holes, some more than 1 billion times the mass of our Sun, appear in the cosmic timeline just a few 100 million years after the universe began. According to our understanding, they simply don't have enough time to grow that big, that fast. So how did they form? Did they skip the slow process of stellar collapse and leap directly into existence through the collapse of massive primordial gas clouds? Or were they seeded by the death of ultramassive first-generation stars unlike anything we see today? Again, we don't know. But the questions drive us. One of the most mind-bending recent discoveries is the possibility that every particle in the universe is somehow encoded in the fabric of spacetime near a black hole. Some physicists have proposed that the entropy of a black hole, the measure of information it holds, is proportional to the surface area of its event horizon, not its volume. This is shocking. It's like saying everything inside your house, down to the molecular level, could be fully described just by examining the outer walls. It defies intuition and yet holds under the rigorous scrutiny of mathematical theory. This has led to the deeper concept that our universe itself may be holographic, that the 3D world we perceive might be a projection of information stored on a distant 2D surface. It's not a metaphor. It's a serious line of theoretical inquiry, with support from string theory and black hole thermodynamics. If proven, it would revolutionize not only physics but philosophy. What is real? What is illusion? Where do you draw the line? And then there's the growing awareness that black holes might not even be the Ultimate endpoint of matter. Some researchers propose exotic alternatives to the singularity, such as the Planck star, a hypothetical object born when quantum gravity halts the collapse of a black hole before it becomes truly singular. Instead of compressing into a point of infinite density, matter could bounce back, perhaps exploding into a new phase of spacetime. This could even hint at a cyclic model of the universe: collapse, rebound, expansion, collapse again. Which raises the question, what if the Big Bang wasn't the beginning? In our most cutting-edge cosmological models, there's growing speculation that our universe is just one bubble in a vast multiverse, each bubble governed by its own physical laws. Some of these universes might be like ours. Others might be utterly alien: no stars, no atoms, no time as we know it. In such a multiverse, black holes could act as bridges, wormholes, linking one bubble universe to another. This isn't idle fantasy. The math allows for it. And the implications are staggering. If true, then falling into a black hole might not be a one-way ticket to destruction but a form of cosmic recycling. A portal to somewhere, or something else. But this idea comes with consequences. If black holes are doors to other universes, then where are their event horizons? Are there black holes in those universes too? Could information from our universe influence the formation of others? Could civilizations, far older, far more advanced than ours, have found ways to navigate or even create such bridges? We're not just asking how black holes work anymore. We're asking whether they are tools. Whether they are natural engines of cosmic engineering. Imagine a civilization so advanced it could build structures around black holes to harness their rotational energy, a theoretical concept called the Penrose process. Or a Dyson sphere-like construct orbiting a black hole instead of a star, capturing energy from the surrounding accretion disk and Hawking radiation. These civilizations would be Type 2 or Type 3 on the Kardashev scale, not just using the energy of a planet or star, but of entire galaxies. These are civilizations that might not even use matter as we understand it. They could exist in plasma states, quantum networks, or even dark matter structures. Which begs the question, if such civilizations exist, or existed, how would we recognize them? Would their structures be indistinguishable from natural cosmic phenomena? Could some of the weird gravitational anomalies we observe be the remnants of their engineering? Even more chilling, would we even be capable of detecting them at all? It's entirely possible that advanced intelligence becomes indistinguishable from natural law. A hyper-civilization might encode itself into black holes, using them as storage devices, each gram of matter containing as much information as 1 trillion modern supercomputers. We may already be living in a universe that is, in part, the result of intelligent design, not in a mythological sense, but in a deeply scientific one. A universe modified, seeded, and nudged along by the remnants or intentions of minds far beyond ours. We're drifting into territory that blurs science with metaphysics, but this is where the mysteries of space lead us. It's not just about what we know, but about what we can know. Our brains, marvelous as they are, evolved to hunt, gather, build, and imagine. But are they capable of comprehending the full scope of a 12-dimensional multiverse? Or timeless quantum states? Or eternity? Perhaps not fully. But still, we try. And that brings us to one of the most haunting mysteries of all. Why is the universe comprehensible at all? Why is it governed by laws, beautiful, symmetrical, often expressible through elegant mathematics? Why does it follow patterns we can decode, even partially? If the universe were truly random, we would expect chaos. But instead, we see order emerging from disorder, structure from entropy, stars from gas, life from chemicals, minds from matter. And perhaps that's the most mysterious thing of all, that in a cold, expanding cosmos filled with black holes, dead stars, and silent galaxies, there exists this one blue planet, where atoms came together not just to survive, but to wonder. We are the product of the universe becoming aware of itself. So when we look at black holes, we're not just studying astrophysical objects. We're staring into the very limits of our knowledge, the edge of science, the shores of the cosmic ocean. We may never enter one. We may never fully understand what they are or what lies beyond. But in asking, in imagining, in reaching, perhaps we fulfill the purpose of consciousness itself. Because the universe is not just vast, it is mysterious. And the mystery is what makes it beautiful. And in that beauty, there is a tension, a quiet, almost sacred contradiction. The universe, indifferent to our presence, also allows for our curiosity. It does not bend its rules for us, and yet those very rules are decipherable through the language of mathematics and observation. It is in black holes where this contradiction reaches its crescendo. Here, in the most violent and alien regions of the cosmos, where time ceases and space folds in on itself, we encounter the most urgent, unsolvable riddles of existence. But the mystery doesn't only lie in what black holes are, but in what they do to the world around them. Let's talk about the phenomenon of spaghettification. This is not science fiction. It's an observable prediction made by general relativity. If you were to fall into a stellar mass black hole feet first, the gravity acting on your feet would be exponentially stronger than on your head. You would be stretched, atom by atom, into a long, thin strand. Ripped apart, yes, but not in a single moment. Rather, your body would be elongated so drastically that even the particles that made up your cells would be separated in what scientists grimly call tidal disruption. It's a gruesome fate, yet eerily elegant in its predictability. It reminds us that black holes don't just bend space and time, they deform everything that enters their domain. And this is a small black hole, a few solar masses at most. In contrast, supermassive black holes like Sagittarius A are so enormous that the tidal forces at their event horizons are actually much weaker. You could pass the threshold without even noticing, until it's too late. You wouldn't be torn apart immediately. You'd fall peacefully, silently, deeper into the dark, without any possible way to communicate with the universe you just left behind. There's something deeply poetic about that, a silent crossing, unnoticed, irreversible. And yet, there's another strange twist in this story. The matter that falls into a black hole doesn't disappear immediately. Instead, it forms a superheated disk of plasma known as an accretion disk that spirals in slowly, shining brilliantly in X-ray light. These disks are some of the brightest objects in the universe, paradoxically surrounding the darkest. From these hot maelstroms, relativistic jets can erupt, beams of charged particles shot out from the black hole's poles at nearly the speed of light, stretching across galaxies. No one fully understands how these jets are formed, but they are among the most powerful forces known. It's as if the black hole, even as it consumes, also creates. From destruction comes structure. From silence, thunder. This duality extends even further when we consider their cosmic role. For a long time, black holes were thought to be nothing more than exotic endpoints for massive stars. But now we understand that they are central architects of galaxy formation. Observations show a strong correlation between the mass of a galaxy's central black hole and the properties of its stellar bulge. Somehow, black holes influence the growth of galaxies millions of times their size. How? We're still working that out. But it suggests a hidden order, a cosmic balance, gravity sculpting matter into spiral arms and elliptical cores, all centered around a point of infinite compression. And then, of course, we have the echoes. Recent research into gravitational wave events has raised a fascinating possibility. After two black holes merge, the newly formed black hole may not immediately settle into silence. Instead, it might echo, subtle gravitational ripples, like the ringing of a cosmic bell. Some claim to have detected these echoes, though the evidence is still under debate. If confirmed, it could point to quantum corrections at the event horizon, a clue that our classical view of black holes is incomplete. It might mean the horizon isn't a clean one-way boundary, but a fuzzy quantum veil where information is preserved, altered, or delayed. Such ideas inch us toward a unifying theory of everything, the long-sought fusion of quantum mechanics and general relativity. That theory might be string theory. It might be loop quantum gravity. It might be something entirely unexpected. But it will almost certainly pass through the crucible of black hole physics. Like a mythic gatekeeper, the black hole stands between what we know and what we cannot yet grasp. Let's consider a more radical idea, black hole cosmology. There is a hypothesis that suggests every black hole creates a new universe on the other side of its event horizon. From our side, we see only the gravitational pull, the irreversible collapse. But beyond it, a white hole, an expanding region of spacetime not bound by our universe's limits. In this model, universes give birth to other universes through black holes. The parameters of physical law, gravity strength, particle masses, dark energy, could slightly mutate with each cosmic generation. Natural selection on a cosmological scale. Universes that produce many black holes create many offspring and thus persist, while those that do not fade away. If that sounds too poetic to be science, remember, Darwin's theory of evolution was once dismissed as naive speculation too. This framework is called cosmological natural selection, and while it's not proven, it opens a doorway to viewing black holes not just as endpoints, but as beginnings. And perhaps this is the greatest transformation in our perception of the cosmos. Once, we saw black holes as terrifying anomalies, glitches in nature's system. Now, we suspect they are central to the very architecture of reality. Not mistakes, but mechanisms. Essential components in a cycle of creation and destruction that goes far beyond our lifespans, or even the age of our own universe. Let's not forget that there are black holes possibly wandering between stars and galaxies, rogue entities, unbound to any one system. Imagine a black hole, invisible, silent, gliding through interstellar space. You wouldn't know it was approaching until it was too late. It would pull on the Oort cloud, disturb comets, perhaps even bend the orbit of Neptune. It might swing through the solar system over millions of years, unnoticed by any civilization without precise gravitational mapping. And what if, deep in the future, humans could tame a black hole? There are genuine discussions, among the most theoretical of futurists and physicists, about civilizations using black holes as energy sources. Hawking radiation, while incredibly weak for large black holes, becomes significant for microscopic ones. A small, artificial black hole, if it could be created and stabilized, could power an entire planet. More than that, it could serve as a clock, a data vault, even a time dilation device for future interstellar travel. Yes, we are eons away from such feats. But so were we, once, from fire, from steel, from flight, from decoding DNA. Progress doesn't always move in straight lines, but it never truly stops. And every great leap begins with curiosity. In the end, perhaps this is the true role of the black hole in human consciousness. Not as a destination, but as a mirror. They show us what we don't yet understand. They reveal the limitations of our theories and invite us to tear them down, build again, imagine anew. They force us to confront the boundaries of meaning, mortality, and even existence itself. They ask questions in a language we're still learning to speak. So keep looking up. Keep wondering. For every photon we catch from a distant galaxy, every wave we record in spacetime, every equation scribbled on a chalkboard brings us closer, not just to black holes, but to ourselves. Because in the end, the black hole does not only consume, it illuminates. And while it may seem paradoxical that something defined by its darkness can serve as a source of illumination, black holes do exactly that, not in the way a candle lights a room, but in how a question lights the path to discovery. Each revelation we glean from these enigmatic entities is not just about them. It's about the fabric of everything, about gravity, time, information, entropy, and ultimately, the human urge to understand what we were never meant to survive long enough to question. In truth, black holes are the crucibles in which our most advanced science is tested. They are the proving ground of theories. If a physical law works near a black hole, it is likely universal. If it breaks down, the law must be rewritten. They are the stress test of the cosmos, merciless, unrelenting, and honest. Yet for all their destruction, black holes have become cosmic laboratories. Consider the collisions that give rise to gravitational waves. When two black holes spiral into each other, they do so with a kind of grace that belies their immense violence. The gravitational waves they emit carry with them the signature of the masses, spins, and energy loss of the system. From Earth, using instruments like LIGO and Virgo, we can detect these waves and literally listen to space. Not metaphorically, the data can be converted into audible sound. We've heard the final scream of merging black holes, chirping like the echo of creation itself. There's something incredibly humbling about this. We have ears for the music of the universe, not just eyes. And with each new detection, we learn more, not just about the black holes themselves, but about the distribution of matter in the universe, the population of massive stars, the speed of cosmic expansion. Black holes, in their death dance, become beacons. We've also begun mapping the environments around them. With the Event Horizon Telescope, scientists have captured the silhouette of a black hole, not just once, but now multiple times. The fuzzy, golden ring we saw in 2019 around M87 was a milestone in observational astronomy. For the first time, humanity had peered directly into the abyss and returned with an image. This wasn't an artist's rendering. It was real, built from petabytes of data stitched together by a network of radio telescopes across the globe. And yet, that image only scratched the surface. Behind that blurry ring is a turbulent story of magnetic fields, accreting matter, plasma jets, and relativistic winds. There's an entire universe of complexity dancing just outside the event horizon. By studying the polarization of light, astronomers have begun to untangle the magnetic geometry of these regions, getting a sense of how jets form and why they aim the way they do. These are not passive drains in the fabric of space. Black holes influence. They direct the very shape and activity of the galaxies that house them. Even our own Milky Way, as quiet as it seems, is slowly feeding its central black hole. Occasionally, clouds of gas wander too close, and flares of energy burst from the galactic core. These are the whispers of Sagittarius A, hints of an ancient appetite not yet forgotten. And when our galaxy eventually merges with Andromeda billions of years from now, the two central black holes will also merge, shaking the very structure of space-time itself in a gravitational cataclysm. It's important to realize just how small we are in this story, and yet, how incredibly aware. We live in a universe that operates on scales so vast they defy comprehension, and yet, in the quiet corners of one pale blue planet, we've managed to piece together the equations that describe it. We've built machines that listen to the cosmos and capture its stories. That is nothing short of miraculous. But this miracle comes with a cost in complexity, in uncertainty, in humility. Because for every answer, 10 more questions rise. What happens to time inside a black hole? From the outside, an object falling toward the event horizon appears to slow down, frozen in place forever. But from the falling object's perspective, it crosses the threshold in finite time. So which is it? Both. Neither. Depends on the frame of reference. This relativity of experience is not just theoretical, it is deeply real, built into the very structure of the universe. And then there's the question of entropy. According to the second law of thermodynamics, entropy, the measure of disorder, always increases. Black holes, despite their simplicity, seem to have enormous entropy. The larger the black hole, the greater its entropy, suggesting it holds an immense number of possible microstates, ways that its constituent particles could be arranged, even though we can't see them. So where is this information stored? On the horizon? Inside? Does it matter? This question, like so many others in black hole physics, forces us to examine not just what we observe, but how we define knowledge itself. Take the firewall paradox. Some quantum physicists believe that instead of a smooth crossing at the event horizon, infalling matter may encounter a wall of high-energy particles, a firewall, which would obliterate it. This contradicts the equivalence principle of general relativity, which says you shouldn't feel anything special as you cross the horizon of a large black hole. But quantum theory says otherwise. So which one is right? No one knows. The debate rages on. This is what makes black holes beautiful. They are not just cosmic objects. They are crucibles for our understanding, testing the limits of physics, logic, and imagination. They hold up a mirror and ask, how far are you willing to go to understand the truth? And sometimes, that mirror reflects us in unsettling ways. The sheer indifference of a black hole, its lack of care, its erasure of information, its ruthless obedience to gravity, is a reminder that the universe is not built for comfort. It is built for balance, for structure, for rule, not kindness. And yet, from that cold calculus arises wonder. From the void comes awe. From the silence, questions. Because black holes are not simply cosmic garbage disposals. They are the punctuation marks in the story of the universe. They are the commas, the pauses, the endings that lead to new beginnings. When stars collapse, black holes are born. When black holes merge, galaxies shudder. When black holes evaporate, if Hawking is right, they will vanish with a final whisper, leaving behind, what? Radiation? A remnant? A doorway? We are still listening. And we will keep listening. Because in every gravitational wave, in every flicker of X-ray light, in every whisper from the abyss, we find not just data, but destiny. A calling to venture deeper, to question harder, to never settle. The black hole will never give us its secrets freely. But that's the point. We must earn them. And perhaps that struggle, the effort to comprehend the incomprehensible, is what defines our species more than anything else. We are not the strongest, not the fastest, not even the most enduring life forms on our own planet. But we are the ones who ask why. The ones who climb out of our gravity wells and stare into the abyss, not just out of necessity, but out of wonder. And black holes, they respond to that wonder. Not with answers, but with provocations. Let's return to one of the deepest puzzles, the black hole information paradox. It's not just an academic debate, it goes to the heart of whether reality is ultimately deterministic. In classical physics, if you know the present state of a system, you can predict the future and retrodict the past. Everything is governed by laws. Nothing is truly lost. But when a black hole swallows something, say, a spaceship or even a single atom, what happens to the quantum information carried by that object? Hawking's original formulation of black holes in the 1970s suggested that anything falling in is lost forever, erased when the black hole eventually evaporates. But this breaks the rules of quantum mechanics, which insist that information is never destroyed. This conflict triggered a battle that has lasted nearly 5 decades, with the world's most brilliant physicists offering competing ideas. Maybe the information is stored on the event horizon. Maybe it leaks out slowly over time via Hawking radiation. Maybe it's encoded in subtle correlations in the outgoing radiation. Maybe we're completely wrong about how quantum gravity works. Even today, there's no full consensus. But the paradox has become more than just a puzzle. It's a guiding torch, leading the way toward a future theory that might finally reconcile Einstein's smooth, geometric spacetime with the jittery, probabilistic dance of quantum particles. In that future theory, call it a theory of everything, a grand unified theory, or simply the truth, black holes will likely serve as the key. And that key may unlock more than just scientific understanding. It may force us to reconsider reality itself. Take, for example, the idea of black holes as computational engines. Physicist Seth Lloyd once proposed that the universe is essentially a quantum computer, that every physical interaction is a kind of computation. In that view, black holes are not just massive celestial bodies, they're the ultimate computers. They perform calculations at the limits of physical possibility. Every Planck area on the surface of a black hole, each microscopic square no larger than 10 to the power of -66 cm squared, holds a bit of information. And when you add them all up, the surface of a black hole contains more data than anything else in the known universe. In essence, a black hole may be the densest hard drive imaginable, storing not only mass, but memory. This isn't science fiction. It's grounded in the mathematics of entropy and thermodynamics. It leads us to the holographic principle again, the unsettling notion that what we perceive as three-dimensional reality may, at its core, be a projection of information encoded on a distant two-dimensional surface. It's a reversal of everything we thought we knew. Not unlike Plato's cave, we may be watching shadows on the wall and mistaking them for the truth. And yet, there is something deeply spiritual in all of this. Spiritual in the sense of scale, of humility, of the sublime. When we talk about black holes, we're not merely discussing gravitational wells or entropy equations. We are confronting the infinite. The boundary between life and death, presence and absence, order and chaos. In literature, in philosophy, in myth, the abyss has always symbolized the unknown. And in modern astrophysics, that symbol has taken form in the black hole. We speak of falling into one, but what does that mean? What if consciousness fell in? What if an AI did? What if a message, encoded in neutrinos or gravitational waves, could be sent through one and survive? Could we ever receive it? Could we decode it? Science fiction has long been fascinated with this concept. In Interstellar, the protagonist descends into a black hole and emerges into a 5-dimensional construct where time is physical and love becomes a literal force. It was a poetic interpretation, but rooted in real physics, advised by Kip Thorne, a Nobel laureate and expert in gravitational theory. That's what's extraordinary. The science has reached a point where even our wildest fictional dreams are no longer absurd, but possible. Not probable, perhaps, but not forbidden. And what of the future? If humanity survives long enough, if we conquer our own self-destructive tendencies, transcend the limitations of our biology, and evolve into something post-human, black holes may become tools, not just mysteries. We may use them for travel, energy, even computation. Some speculative models suggest that wormholes, theoretically connected to black holes, could offer shortcuts across the universe. And while wormholes remain unproven, the equations allow them. The universe, once again, whispers, try. But there is danger here too. Black holes, like all powerful forces, do not care about intention. They are impartial, unforgiving. We already fear asteroids and gamma-ray bursts, but a wandering primordial black hole, no larger than a mountain, yet with more mass than the moon, passing through Earth would spell annihilation. Not with an explosion, but with a silent gravitational ripple that tears us apart at the molecular level. And we might not even see it coming. There's also the risk in experimentation. Theoretical fears were raised when the Large Hadron Collider was first activated, concerns that it might create microscopic black holes. Scientists dismissed these worries, explaining that such black holes would evaporate instantly due to Hawking radiation. But the fear speaks to a larger truth. The line between understanding and danger is thin. And in exploring the boundaries of existence, we must tread carefully. Still, we explore. We must. Because black holes are not the end of the road. They're a bend in the path. A curve in the spiral staircase of knowledge. A veil that hides not oblivion, but transformation. They teach us that death in the universe is rarely final. Stars die, yes, but they leave behind neutron stars, white dwarfs, black holes. They scatter heavy elements, carbon, oxygen, iron, into space, seeding new systems, new worlds, new life. Without supernovas, there would be no gold in your jewelry, no calcium in your bones, no oxygen in your lungs. Without black holes, perhaps there would be no galaxies. No gravitational glue to bind stars into spirals and clusters. No crucible to force matter into the complexity that births stars, planets, and consciousness. So, when we look into a black hole, we're not gazing into death. We're looking at a doorway. A symbol of what we don't know yet, and a promise that there's more to learn. Because the greatest mystery of black holes isn't what lies inside them. It's that they exist at all. And that existence, undeniable, incomprehensible, yet vividly observable in their effects, places black holes at the very core of the cosmic narrative. They are both ancient and timeless. They outlive stars. They distort our concept of before and after. They anchor galaxies and stretch the laws of physics until they begin to unravel. But let's not forget, black holes are part of the universe, not outside of it, not above it, not separate from it. They are born in the same cosmic crucible that forged our sun, our planet, our atoms. They are not alien intrusions but natural outcomes. When enough mass collapses, when gravity reigns over all other forces, a black hole must form. It's inevitable. And inevitability is something the universe understands very well. Yet, the more we learn, the more exceptions we discover. Consider the idea of naked singularities, singularities not hidden behind an event horizon. General relativity, in its classic form, suggests that every singularity must be cloaked by an event horizon, a kind of cosmic modesty, preventing the singularity's infinite weirdness from corrupting the outside universe. This is called the cosmic censorship conjecture, proposed by Roger Penrose. But it's still a conjecture, and in certain theoretical models, naked singularities could exist. That would be a true disaster for physics as we know it. Why? Because without the event horizon acting as a boundary, the breakdown of the laws of physics inside the singularity would bleed out into the rest of spacetime. Cause and effect could collapse. Time could fragment. Predictability, the bedrock of science, would be lost. We would no longer have a universe governed by rules, but one susceptible to chaos at its most fundamental level. Thankfully, we have not observed a naked singularity. But the math says it's possible. So again, the cosmos dares us. Can you prove this is impossible? Can you understand why? In this, black holes are more than puzzles, they are provocations. They ask us to test the limits of our knowledge, not to defeat us, but to elevate us. To push science not as a static body of facts, but as a living, breathing pursuit of truth. And in this pursuit, new tools are emerging. We're entering an era of multi-messenger astronomy, where cosmic events are not just seen, but also heard, felt, timed, and even simulated. A single event, such as the merger of two neutron stars, can emit gravitational waves, gamma-ray bursts, X-rays, and visible light. Black holes, though often dark, play starring roles in these multimodal cosmic events. By observing from multiple channels, gravitational, electromagnetic, neutrino-based, we are building a more complete picture of how black holes form, interact, and influence the universe. This also means we're getting better at prediction. With machine learning and AI, astronomers can sift through immense datasets to identify black hole candidates, understand accretion patterns, and even predict potential gravitational wave events. The combination of human intuition and artificial computation is beginning to peel back layers of the cosmos once thought impenetrable. But let's take a moment to reflect on how far we've come. Just a century ago, black holes were theoretical ghosts, solutions to equations that many believed could never exist in nature. Einstein himself resisted them. To him, the idea of matter collapsing into a point of infinite density was too absurd. And yet, his equations, cold, indifferent, mercilessly precise, demanded it. Today, not only do we accept the existence of black holes, we have photographed their silhouettes, measured their spins, tracked the stars they whip around at relativistic speeds, and heard their collisions from across the universe. This isn't just progress. It's a revolution in consciousness. And as we look forward toward the next generations of telescopes, the James Webb Space Telescope, the Vera Rubin Observatory, the Einstein Telescope, and beyond, we prepare to enter the Deep Time Observatory. We're not just looking at where things are, but how they evolved. We're studying the universe not as a snapshot, but as a story. And black holes are among its most dramatic chapters. We may one day witness a black hole being born, not just inferred from a supernova remnant, but seen in real-time collapse. We may observe stars spiraling into one, lighting up with bursts of radiation as they're shredded. We may map the flow of time around their edges, see the gravitational redshift with our own instruments, watch photons dance along the edge of nothingness. And eventually, if we're bold, if we're still here, we may send something in. A probe, a camera, a ship, an AI designed to survive the tidal forces, riding the event horizon like a surfer on the edge of a wave. What could it see? What could it send back? Maybe nothing. Or maybe everything. Maybe it wouldn't return at all. But maybe, just maybe, what it experiences would change everything. Not all at once. Not with a flash of revelation. But with slow, methodical transformation. Just as black holes reshape space and time, the knowledge we gain from them reshapes us. Because in the end, the mystery of black holes is the mystery of boundaries, and of what lies beyond them. The boundary between known and unknown. Between classical and quantum. Between something and nothing. Between this universe, and what may come after. They are not just celestial bodies. They are thresholds. Crossing them may not be possible, or survivable. But understanding them? That's what it means to be human. To look into the darkness and imagine light. To face the void and listen. To hear nothing, and still answer with curiosity. Because in every shadow, there is the outline of a deeper truth. And in every black hole, the promise, the challenge, of a universe still unfinished. And so we return, again and again, to the edge of the abyss, not because we expect the abyss to answer us, but because the act of questioning is what propels us forward. The black hole is not the end of knowledge. It is the event horizon of possibility. A limit we press against, trying to see through, trying to go beyond. But the deeper we go, the more we realize something profound. Black holes are not simply astrophysical objects. They are philosophical touchstones. Their existence forces us to confront ideas that shake the foundation of what we assume to be real. Take, for instance, the arrow of time. In most physics equations, from Newton's laws to Maxwell's equations to even Schrödinger's wave equation, time is symmetric. There is no built-in distinction between past and future. But our experience tells us otherwise. Eggs break, they don't break. Smoke rises, it doesn't gather and form a log. We remember the past, not the future. This is the arrow of time, and black holes may be intimately tied to its existence. When matter falls into a black hole, entropy increases. The black hole grows. This irreversible process mirrors the second law of thermodynamics, that entropy tends to increase over time. In fact, some physicists believe that the gravitational arrow of time, dictated by black hole dynamics, may be the deeper cause of the thermodynamic arrow we experience every day. In this view, the flow of time is tied not just to temperature or disorder, but to gravity and collapse. Time moves forward because black holes grow. But this presents an unsettling idea. If a black hole can evaporate via Hawking radiation, shrinking over eons, what does that mean for the arrow of time? Does it reverse? Does it fizzle out? Or does the universe itself face an eventual end where all black holes have evaporated, all matter has decayed, and only low-energy radiation remains? A dark, silent, heat-dead cosmos? This bleak scenario is known as the heat death of the universe, and it is currently one of the leading candidates for the universe's ultimate fate. In this future, black holes are among the last to go. Long after the stars have burned out, long after galaxies have drifted apart, the black holes will remain, slowly evaporating into the void over unimaginable spans of time, 100 years or more. And when the last black hole evaporates, nothing. No light. No heat. No structure. Just a cold, infinite stillness. This is perhaps the greatest cosmic irony. Black holes, born from collapse and chaos, will be the final echoes of cosmic structure. Their evaporation, quiet, slow, inevitable, is the universe's final breath. But what if that's not the end? What if, hidden within that evaporation, within the quantum flickering at the edge of the event horizon, lies the seed of a new beginning? Some speculative theories propose that black holes could be white holes in reverse, objects that eject matter and energy instead of absorbing it. In certain models of loop quantum gravity, when a black hole reaches a certain density, it could undergo a quantum bounce, reversing into a white hole and spewing out all the information it ever contained. A kind of cosmic recycling. A rebirth. More radically, some physicists entertain the notion that every black hole may birth a new universe within it, a daughter universe, connected to our own only through the singularity. In this view, our own universe may be the interior of a black hole that formed in a parent universe, and every black hole in our cosmos might contain a whole new reality beyond our comprehension. If this is true, then black holes are not the tombstones of stars, they are the wombs of creation. And suddenly, our place in the cosmos takes on new meaning. We are not just stardust, we are born of processes that may echo across multiple universes. We are the observers of a lineage that stretches beyond the horizon of our own sky. A cosmic ancestry written not in DNA, but in entropy, gravity, and curvature. The scope is dizzying. The implications, staggering. But even as we chase these grand ideas, black holes remain stubbornly personal. They appear in our dreams, our myths, our metaphors. The void we fall into in nightmares. The black hole of grief, of memory, of emotion. The sense that something has been taken from us, that something is unreachable, and yet, still felt. Carl Jung once said that the shadow is where we hide our darkness, our fears, our unacknowledged truths. In this way, black holes are the shadow of the universe. Not evil, not malevolent, but essential. They are where the light fails, yes, but also where meaning gathers. The universe hides its most powerful processes in darkness. Maybe that's why we're drawn to it. Maybe we see in black holes a reflection of our own deepest selves, the parts we don't understand, the questions we fear to ask, the truths too powerful to face directly. And yet, face them we must. Because we are not passengers in this cosmic voyage. We are navigators, explorers, storytellers. When the first humans looked up at the stars, they didn't see gravitational collapse or accretion disks. They saw constellations etched in hope. Now, we see black holes. But perhaps that too is a kind of hope. Hope that even in darkness, there is knowledge. Hope that even in silence, there is message. Hope that even in the greatest collapse, something is born. And so we continue. Watching. Listening. Building instruments that stretch our reach to the edge of time. Crafting theories that bend our minds around curvature and entropy. Dreaming of ships that might one day dance along an event horizon, riding the gravity well like a wave. We do this not because the answers will come quickly. Not because the truths are simple. But because the pursuit itself is sacred. The black hole will always hold some secrets. That is its nature. But so too is ours, to seek them. And we seek not just with instruments and equations, but with imagination. Imagination is what allowed Einstein to visualize riding alongside a beam of light, what led Hawking to contemplate the slow whisper of radiation escaping the unescapable, what fuels today's theorists as they model exotic geometries like Calabi-Yau manifolds or simulate baby universes branching from collapsing stars. In black holes, the boundary between science and imagination blurs, not because we forsake rigor, but because the questions they demand are so vast, no single approach can hold them. And that imagination doesn't reside solely in observatories or university halls. It lives in the minds of children looking up at the night sky, wondering what's out there. It lives in artists painting the curve of a galaxy, in poets invoking the metaphor of falling, of being consumed, of becoming something else entirely. Black holes stretch our language as much as our physics. They invite us to speak not just in formulas, but in awe. Consider what it means for space itself to fall into a black hole. Not just light. Not just matter. But space, the very fabric that defines where things are. Near a black hole, this fabric is pulled, twisted, accelerated inward. The coordinates themselves collapse. The closer you get to the event horizon, the more space behaves like a waterfall, rushing inward faster and faster, until even light can't swim against the current. This is the concept of space-time as a river, a useful analogy proposed by some physicists to visualize the strange behavior near event horizons. In this analogy, space is flowing, and a black hole is like a waterfall where the current becomes so fast that not even light, the fastest thing in the universe, can escape the pull. If you were in a spaceship, outside observers would see you slow down as you approached the event horizon, infinitely slowly, in fact. But from your perspective, you'd fall through it in finite time, experiencing nothing unusual at the moment of crossing, depending on the size of the hole. But what lies beyond that threshold remains one of the most tantalizing unknowns in all of science. Some theories suggest a smooth passage to a singularity, a point of infinite density where the laws of physics as we know them simply break down. Others suggest a firewall, a violent boundary of quantum energy that would destroy anything entering, contrary to general relativity. Still others imagine a portal, a wormhole, a tunnel to another region of spacetime, or even another universe. No one knows. And perhaps we never will. Perhaps the information is scrambled in a way we cannot yet decode. Perhaps the journey beyond the horizon is one we are destined never to make physically, only mathematically, philosophically, metaphorically. But even that journey matters. Because in pushing against that limit, we refine what we do know. We invent new mathematics, new instruments, new questions. We unify the distant disciplines of quantum field theory and cosmology, of information theory and geometry. We illuminate more of the cosmic canvas. And in doing so, we realize something else. The black hole is not unique in being mysterious. It's just the most extreme. But mystery is the default state of the universe. Think of dark matter, this invisible substance that outweighs ordinary matter 5 to 1, yet has never been directly detected. Or dark energy, the force accelerating the expansion of the universe, whose nature is entirely unknown. These components, combined with black holes, make up over 95% of the cosmos. Everything we can see, planets, stars, dust, galaxies, is just a sliver, a trace. And yet, it is in that sliver that consciousness arose. Here, on a pale blue dot orbiting an average star in an ordinary galaxy, matter organized itself into minds. Minds that could wonder. Minds that could question gravity, write equations about entropy, build observatories to peer across billions of light years. Minds that could name the darkness, and not turn away. It is, perhaps, the greatest mystery of all, that the universe is not only knowable, but that it gave rise to beings capable of knowing. That the cold equations of physics led to warmth, to curiosity, to exploration. That black holes, those monstrous engines of gravity, would one day be studied by creatures made of dust, with hearts that beat and eyes that gaze upward. And so we keep watching. Not because we believe we'll answer every question, but because every question brings us closer to the truth. Not an absolute truth, not a final answer, but a deeper truth, one that connects everything. One that reveals the hidden architecture of reality, one brick at a time. And maybe that's the real function of black holes. Not to hide, but to reveal. By pushing us to the edge of knowledge, they force us to stretch our minds, to rethink our assumptions, to create new science, new art, new meaning. They are the ultimate challenge, and the ultimate invitation. Because at the end of it all, black holes remind us of one vital truth: the universe is not just vast and violent. It is intelligent, structured, alive with patterns, full of symmetries and surprises, governed by laws that we can learn, even if we never fully grasp them. And within that infinite complexity, there is still room for us. We, who question. We, who imagine. We, who reach into the void not to conquer it, but to understand our place within it. The black hole does not answer, but it asks, with perfect silence. And in our efforts to reply, we discover who we are. And who we are, when measured against the vastness of space and the silence of black holes, is not insignificant, but unfinished. Every time we stretch the boundaries of what we know, we are reshaping not just our science, but our very identity. We go from stargazers to starmakers, from wondering what the stars are, to uncovering how they die and what they leave behind. Black holes, those dense, quiet, gravitational remnants that hold in their gravity the echo of cosmic explosions. It is through this lens that we must view our species' future in space. Because black holes, for all their mystery and terror, may also be gateways. Not necessarily in the science fiction sense of wormholes or time travel, although those remain theoretically plausible, but gateways of understanding. They are where physics bends, where language stutters, and where our tools of logic and math are tested to their absolute limits. One of the greatest tools in that pursuit is simulation. We cannot yet travel to a black hole, but we can recreate its physics in supercomputers. These simulations allow us to visualize accretion disks, watch magnetic field lines twist and break, simulate jets of matter screaming out at near light speed, or map the moment when two black holes merge into one. These visualizations are not merely educational. They help us predict, test, and interpret the signals we receive, from gravitational wave chirps to X-ray flashes. But there's something more here. Something that goes beyond the mechanics. When we simulate black holes, when we stare at those rendered swirls of light around the darkness, we're not just seeing data. We're seeing stories. The death throes of stars. The collisions of titans. The aftershocks of cosmic events that occurred millions, sometimes billions, of years ago. We are time travelers in a way. Receivers of ancient messages carried on the backs of photons and gravitational waves. The Event Horizon Telescope, EHT, gave us one such message in 2019, the first actual image of a black hole silhouette. A blurry, golden ring, brighter on one side because of the Doppler effect, as matter orbits near the speed of light, surrounding a dark center, the shadow cast by the event horizon. That black hole resides in the heart of the M87 galaxy, 53 million light-years away. And yet, we saw it. It was a moment that transcended science. It was art, history, poetry, a mark in the cosmic ledger that said, we were here, and we looked into the dark. That's what makes black holes so captivating, not just their mystery, but their invitation. They dare us to approach, to test ourselves. And perhaps more than anything, they remind us of scale. Scale of distance. Of time. Of power. A single black hole can weigh billions of times more than our Sun. The one at the center of the Milky Way, Sagittarius A, is relatively small by supermassive standards, but still has a mass of about 4 million suns. And it has shaped the entire galaxy around it. It's possible that without it, the Milky Way wouldn't even exist in its current form. Black holes don't just destroy, they also organize. They shape orbits, compress matter, influence the evolution of galaxies. They may even regulate star formation. A jet of particles launched by a black hole's magnetic fields can heat interstellar gas and suppress the birth of new stars, or stir that gas and trigger star formation elsewhere. It's almost as if black holes are gardeners of galaxies, planting, pruning, shaping, but in a way so alien to us that we still struggle to see the full picture. But we're learning. Slowly. Patiently. We now know there are different types of black holes. The stellar mass black holes, which form from collapsed stars. The intermediate mass black holes, rarer, less understood, possibly formed through star cluster collisions. The supermassive black holes, anchoring galaxies. And then, maybe, primordial black holes, theoretical remnants from the early universe, possibly created from density fluctuations in the first few seconds after the Big Bang. These primordial black holes are particularly interesting because they could answer multiple questions at once. If they exist, they could account for at least part of the mysterious dark matter that pervades the universe. They could also help us understand the nature of the early cosmos, before stars, before galaxies, before even atoms. They could offer a glimpse into the birth of the universe itself. Some even theorize that tiny black holes, on the scale of atoms or smaller, could be created in particle accelerators like the Large Hadron Collider, if extra dimensions exist. These so-called micro-black holes wouldn't be dangerous, they'd evaporate instantly. But detecting them could validate entire frameworks of theoretical physics, such as string theory or brainworld models. And this leads to one of the most tantalizing questions of all. Are black holes the key to unifying physics? For a century, scientists have sought a grand unified theory, something that merges Einstein's general relativity, the physics of the big and heavy, with quantum mechanics, the physics of the tiny and fast. So far, they've remained stubbornly incompatible. But black holes are the one place where both must apply. Their gravity is immense, relativity, but their size, especially at the singularity, is infinitesimal, quantum. They are natural laboratories for a theory of quantum gravity. In fact, studying black holes has already led to some of the most profound insights in modern physics. The idea that spacetime might be emergent, that information might be holographically encoded, that reality itself might be a projection from a deeper, more abstract structure. The famous holographic principle, born out of black hole physics, suggests that everything inside a region of space can be described by information encoded on its boundary. In other words, what happens in 3 dimensions might be fully represented on a 2-dimensional surface. This is not just theoretical trickery, it's a framework being actively used in attempts to reconcile quantum mechanics with gravity. It's a profound, almost spiritual idea, that reality has a boundary, and that everything we are, thoughts, galaxies, civilizations, might be the shadow cast by deeper truths. But perhaps that is what black holes have always been, shadows. The shadows of stars. The shadows of forces. The shadows of the cosmos itself, cast upon the fabric of space and time. And when we look into those shadows, we are reminded of our own. For in each of us lies a frontier of the unknown. Questions we avoid. Mysteries we fear. Depths we have yet to plumb. The black hole is not just out there, it's in here, in the spaces we have not yet explored within ourselves, as individuals, as a species, as a civilization. And yet, the same force that drives us to study black holes is the one that drives us to grow, to change, to evolve. Curiosity. Wonder. The refusal to accept the limits we've inherited. Even if we never touch a black hole, even if we never fully decode their secrets, they will continue to shape us. Because they remind us that the universe is not finished. It is still unfolding. And so are we. And in that unfolding, of the universe, of ourselves, we find the pulse of something greater than knowledge, a purpose. Black holes are not mere riddles to be solved, they are milestones on a path that stretches far beyond the boundaries of our current comprehension. They remind us that science is not a checklist of facts, but a living, breathing quest, one that evolves with every discovery, every failure, every theory that challenges the last. Consider where we are now. Less than 2 centuries ago, black holes were a mathematical curiosity, a solution to Einstein's equations that seemed too extreme, too paradoxical to exist. The very idea that gravity could become so powerful that not even light could escape felt absurd. But nature is not constrained by what we find plausible. Nature is what it is, and our job is to catch up. Now, we've not only confirmed their existence but have heard their collisions through gravitational waves. We've seen their silhouettes against the light of their own furious consumption. We've measured the spin of their horizons, the oscillations of their mass, the whispers of their evaporation. Black holes are no longer ghosts in equations. They are actors on the stage of cosmic evolution. But with each step forward, new questions emerge. Take the recent observations of black hole mergers by LIGO and Virgo. These detectors pick up the tiniest ripples in spacetime, caused when two black holes spiral into each other and collide. The data they provide is astonishing, confirming Einstein's predictions to a breathtaking degree of accuracy. But they also raise eyebrows. Some black holes seem too massive to have formed from normal stellar collapse. Some spins don't align with the predictions. Some mergers appear to come from environments we didn't think could exist. Are these anomalies? Or are they signs that our models are incomplete? There is even evidence that some black holes may form in ways we don't fully understand, perhaps through multiple mergers, or in dense star clusters, or even through the direct collapse of massive gas clouds without ever forming a star. Each of these mechanisms points to new physics, new astrophysical processes, new ingredients in the recipe of the cosmos. And then, there's the mystery of intermediate mass black holes. For decades, these were the missing link, too big to be stellar, too small to be supermassive. But they seem to be turning up in strange places, in dense star clusters, in the outskirts of galaxies, even wandering in intergalactic space. If they exist in significant numbers, they could help explain how the supermassive giants at galactic centers came to be. Did they grow from these seeds? Were they born in violent chain reactions of collisions and accretions? Or were they always there? That last question opens a door to something deeper. Because if black holes, in some form, predated stars and galaxies, then they may have played a role not just in shaping the structure of the cosmos, but in originating it. This is where we approach the edge of speculative cosmology. The idea that black holes, particularly primordial ones, might have formed in the very early universe, before atoms, before light, before structure, carries profound implications. If they were common, they might explain dark matter. If they were rare but stable, they might still be drifting through the cosmos today, invisible and ancient, like fossils of a previous epoch. Some physicists even suggest that black holes could have survived from a universe before ours, that they are, in some sense, older than time as we know it. And that's where the philosophical weight begins to settle in. Because black holes challenge more than our equations. They challenge our understanding of time itself. Inside the event horizon, the roles of space and time switch. What was a direction becomes a ticking clock. What was a moment becomes a distance. It's a reversal so complete that we can't even visualize it. Our minds aren't built to grasp such geometries. But math doesn't lie. The interior of a black hole is a place where causality bends and all paths lead inward, to the singularity. And yet, that singularity may not be real. Many physicists believe that the point of infinite density is a sign that our equations have broken down, not that the universe literally becomes infinite, but that we need a new theory to describe what's happening. This is where quantum gravity must enter, a theory that merges the smooth curves of general relativity with the jittery uncertainty of quantum mechanics. Such a theory might remove the singularity entirely. Instead of a point of doom, the core of a black hole might be a place of transformation, where information is stored, or bounced, or released in strange, subtle ways. This is the frontier of modern research, and it includes models like a loop quantum gravity, which suggests that spacetime itself is quantized, and that singularities are replaced by a kind of bounce, perhaps even leading to white holes or new universes. A string theory, which proposes that all particles are vibrating strings, and that the singularity is smeared out by the extra dimensions that string theory requires. A firewalls, a controversial idea suggesting that instead of a smooth event horizon, black holes have a searing boundary that incinerates anything that touches it, preserving information but violating general relativity. ER equals EPR, a bold conjecture that entanglement, EPR, and wormholes, ER, are two sides of the same coin, implying that black holes might be connected through space-time bridges formed by quantum entanglement. All of these theories are incomplete. All are speculative. But they point to something astonishing, that black holes are not just places in the universe, but gateways to understanding the universe itself. They are the Rosetta Stones of cosmology, objects so extreme that they expose the cracks in our current theories and force us to develop better ones. And maybe that's the ultimate truth. That black holes are not cosmic monsters to be feared, but cosmic teachers to be respected. They teach us humility, in the face of their power. They teach us curiosity, in the face of their mystery. They teach us resilience, as we struggle to decode them, fail, and try again. And most of all, they teach us that the universe is deeper, stranger, and more wondrous than we ever imagined. That beyond every horizon, literal or metaphorical, there lies more. More to explore. More to understand. More to become. And yet, for all we've discovered, all we've theorized, the black hole remains silent. It gives away nothing easily. It is perhaps the most perfect embodiment of nature's power to both reveal and conceal. At its heart, a singularity, or whatever replaces the singularity in the final, unified theory of quantum gravity, is not just a collapse of matter, but of predictability. The equations that define our understanding of reality, Einstein's field equations, the Schrödinger equation, Maxwell's laws, begin to warp and twist under the crushing density of a singularity, like brittle bones under unimaginable weight. And while we've grown comfortable navigating the universe with the tools of mathematics, logic, and experimental validation, black holes stare back with the stubbornness of mystery. They resist our efforts not because we lack intelligence, but because we are brushing up against the limits of what can be known. We are colliding with the event horizon of human comprehension. But perhaps that's the point. Perhaps the journey isn't about fully conquering these enigmas, but about what we become as we try. Because in trying to understand black holes, we are building more than just telescopes and equations. We are building bridges between the known and the unknown, between disciplines, between generations of scientists, and even between civilizations. In the centuries to come, if we ever achieve the status of a true spacefaring species, colonizing the Moon, Mars, and perhaps even venturing to the stars, it will be, in no small part, due to the very ideas black holes have forced us to grapple with. They are sharpening our theories of time, of gravity, of space-time curvature, of energy and entropy. They are the silent architects of new physics, sculpting our understanding through their elusiveness. Imagine for a moment a future where we are no longer bound to Earth, where we ride fusion-powered starships across interstellar gulfs, and black holes are not just astronomical objects studied from afar but navigational landmarks, power sources, and perhaps even repositories of knowledge. The idea of using black holes as energy sources isn't pure fantasy. The concept of the Penrose process suggests that enormous energy can be extracted from a rotating black hole's ergosphere, the twisted region of spacetime just outside the event horizon. In theory, if a civilization could develop the engineering capabilities to send matter into this region and retrieve it cleverly, it could extract energy far more efficiently than from any chemical, nuclear, or even fusion process. This could one day provide the power needed for megastructures or sustained interstellar travel. Even further, some have theorized that if we understood the mechanics of wormholes, those hypothetical tunnels through spacetime that might connect two distant points via black holes and their theoretical counterparts, white holes, we might learn to cross vast interstellar or even intergalactic distances instantaneously. Of course, this requires not only breakthroughs in physics but access to exotic matter with negative energy density, a substance not yet discovered but mathematically permissible in certain quantum field theories. It is speculative, yes. But so was the notion of heavier-than-air flight before the Wright brothers, or the idea of splitting the atom before quantum mechanics. History has shown that what seems impossible today often becomes inevitable tomorrow. And black holes may not be just about going forward, they may also hold the keys to the past. Some radical theories suggest that if you could survive the tidal forces and avoid the singularity, a journey into a black hole might not be a one-way ticket to oblivion, but a passage to another region of spacetime, a kind of cosmic womb where universes are born. This is the idea behind the black hole cosmology hypothesis, which posits that each black hole might give birth to a new universe on the other side. This would make our own universe a kind of cosmic offspring, born from the collapse of a star in a parent universe. It's an idea that teeters on the edge of metaphysics, but one that is taken seriously by some theoretical physicists because it offers a possible resolution to the fine-tuning problem: why the constants of nature in our universe appear so precisely tuned for the existence of life. If universes evolve through black holes, then only those universes with the right physical laws to form stars, galaxies, and black holes would propagate their cosmic lineage. In this way, black holes are not just endpoints, but engines of cosmic evolution. This changes everything. It forces us to reconsider the very nature of existence, not just our own, but the universe's. Are we living in a vast multiverse, where black holes spawn countless new realities? Are we on the cusp of discovering that reality is a self-replicating, self-organizing system where black holes play the role of cosmic midwives? And what does that say about our place in this grand architecture? Far from being accidents of biology on a small planet in a quiet galaxy, we may be the conscious eyes of the universe, beings evolved precisely in the kind of universe that black holes make possible, to one day understand them. And the closer we look, the more we begin to realize that black holes are not truly alien. They are made of the same matter as stars, as planets, as our own bodies. The atoms that collapsed to form them were forged in stellar hearts, the same stellar crucibles that created the carbon in our cells, the calcium in our bones. They are us, and we are them. This is perhaps the most humbling and the most exhilarating revelation of all. That the things we fear most, the void, the collapse, the oblivion of time, are not just external phenomena. They are part of our shared cosmic story. We are not separate from the universe, struggling to understand it from the outside. We are in it, of it, and for it. And so the search continues. We listen to the gravitational echoes of ancient cataclysms. We refine our models, develop new instruments, build bigger arrays of detectors, push the edges of computational power. We run experiments in colliders, hoping to glimpse the micro-black holes that might flash into being and evaporate in a burst of Hawking radiation. We stare deeper into the cosmos, chasing shadows in distant galaxies and measuring the subtle flicker of light bent by invisible masses. And through it all, we keep asking, what is a black hole, really? Is it a place? A process? A paradox? A doorway? We may never find one final answer. But in the act of searching, we are evolving, scientifically, technologically, spiritually. We are learning to embrace the unknown, to welcome the mystery, to see not knowing not as a deficit, but as an invitation. An invitation to think bigger, dig deeper, stretch farther. In the end, black holes are the cosmic mirror. In them, we see our limits, and our potential. We see the laws of physics pushed to their brink, and the imagination pushed beyond it. We see the violence of collapse, and the quiet majesty of order emerging from chaos. We see beginnings masquerading as endings, and endings unfolding into something altogether new. And most importantly, in black holes, we see ourselves, the only beings, as far as we know, who can look into the abyss and not only wonder what lies within, but dare to find out. And so we continue to stare into the abyss, not as helpless observers, but as active participants in a story older and grander than anything humanity has yet written. For in the depths of space, where light dies and time distorts, we are confronted not only with the mechanics of gravity, but with the raw edges of our own ignorance. It is in these gravitational extremes that we are reminded just how much of the cosmos is still veiled from our understanding, and how rare and precious it is to be a species that cares enough to look. The farther we venture, the more we begin to see that black holes are not just celestial oddities tucked away in distant galaxies. They are woven into the very fabric of cosmic evolution. Without them, galaxies as we know them wouldn't form. Supermassive black holes, in particular, sit at the centers of nearly all large galaxies, including our own Milky Way. They influence the formation and movement of stars, they regulate the flow of gas and dust, and through feedback mechanisms, where their gravitational pull affects star formation, they actually shape the growth and structure of their galactic homes. It's paradoxical, almost poetic. These voids, which consume all light and matter, are also among the key architects of cosmic order. They destroy, yes, but in doing so, they create the conditions necessary for stars, planets, and life. This feedback isn't subtle. When a supermassive black hole is actively feeding, pulling in vast amounts of gas, it heats that material to millions of degrees, releasing immense jets of radiation and particles that can travel for thousands of light years. These jets slam into the surrounding environment, compressing and dispersing gas clouds, triggering or halting the birth of stars. In this sense, black holes are like cosmic thermostats, preventing runaway star formation and helping to maintain a delicate equilibrium in galactic ecosystems. They are both predator and gardener, agents of balance in a universe that constantly teeters between chaos and order. But how do these giants come to be? That remains one of the most persistent and puzzling questions in astrophysics. The largest known black holes, tens of billions of solar masses, seem too massive to have grown from the collapse of ordinary stars, even given billions of years. So where did they come from? One possibility is that in the early universe, shortly after the Big Bang, vast clouds of primordial gas collapsed directly into massive black holes without first forming stars. Another idea is that the first generation of stars, population 3 stars, which were enormous, short-lived, and made entirely of hydrogen and helium, may have ended their lives as massive black hole seeds that grew over time. Whatever their origin, it's clear that supermassive black holes were already in place within the first billion years of cosmic history. We've observed quasars, extremely luminous, distant objects powered by feeding black holes, that existed when the universe was less than a tenth of its current age. That means these monsters grew to enormous size astonishingly fast. How they did so remains an open question, and one that is driving some of the most advanced simulations and observational campaigns of our time. As we build more sensitive telescopes, like the James Webb Space Telescope, which is already peering farther back in time than any instrument before it, we are on the cusp of witnessing the formation of these early black holes directly. For the first time, we may actually observe the cosmic infancy of these gravitational giants, catching them in the act of shaping the early universe. And this won't just tell us about black holes, it will tell us about the first stars, the first galaxies, and the birth of cosmic structure itself. But for every question about the distant past, black holes also raise questions about the far future. What happens to black holes over the lifetime of the universe? Do they simply persist forever, sitting like eternal sentinels at the end of cosmic time? Or do they, too, decay? Enter the idea of Hawking radiation, one of the most elegant and haunting concepts in theoretical physics. Proposed by Stephen Hawking in 1974, it suggests that black holes are not entirely black. Quantum mechanics allows for particle-antiparticle pairs to spontaneously pop into existence near the event horizon. Occasionally, one particle falls in while the other escapes. The result, the black hole loses a tiny amount of mass. Over unimaginable spans of time, this process would cause the black hole to evaporate completely. And how long would that take? For stellar mass black holes, trillions upon trillions of years, long after all stars have burned out, all galaxies have dissipated, and even protons may have decayed. But for smaller black holes, hypothetical primordial ones, for instance, the process could be much faster. In fact, some theorists suggest that if such miniature black holes exist, some could be finishing their evaporation right now, releasing bursts of gamma rays we might just be able to detect. A single such discovery would not only confirm Hawking's theory, but fundamentally reshape our understanding of black holes, entropy, and the ultimate fate of the universe. And therein lies the most sobering implication of all. Black holes might be the last things to die. In the far, cold future, when the cosmos has entered what some call the degenerate era, after the stars have faded, after white dwarfs and neutron stars have cooled into black husks, after matter itself begins to disintegrate, black holes will remain. For eons, they will drift silently through a dark, expanding universe, consuming the last remnants of mass and energy. Then, after unfathomable ages, they too will begin to fade. Not in a blaze, but in a whisper. A slow trickle of energy leaking into the void. Until at last, even they are gone. This is the heat-death scenario, where entropy reaches its maximum, and the universe becomes a dark, cold sea of dilute radiation. No structure. No information. No life. And yet, as we stare down this distant, inevitable future, there is something beautiful in the knowledge that black holes, these ancient, silent behemoths, will have stood as the final guardians of cosmic complexity. That they, too, had lifespans. That they, too, were part of the grand arc of existence. And what a profound arc it is. From quantum fluctuations at the beginning of time to the collapse of stars into infinite density, from the birth of galaxies to the end of time itself, black holes are there, witnessing everything, influencing everything, revealing the very structure of reality. They are not simply endpoints. They are symbols. Symbols of what we don't yet understand, and of our relentless determination to understand it anyway. They are the final questions, and the first hints of new beginnings. And so, in the silent theater of the cosmos, black holes play the role of both narrator and mystery. They don't speak in words or emit light. They speak through gravitational whispers, through the distortion of light that bends around them like time itself bowing to their command. They are the unsolved poem of the universe, verse after verse written in the curvature of space-time, their stanzas hidden behind a curtain we may never fully lift. But in our attempt to read this poem, to decode its rhythm and metaphor, we learn more about who we are than the black holes themselves. Our efforts to study them are not just technological triumphs, they are acts of philosophical courage. It takes a certain kind of audacity to peer into something that, by definition, hides everything. And yet, humanity does it without hesitation. We point our telescopes, our theories, and our dreams toward them. And in return, black holes reflect our deepest questions back at us, like mirrors forged in the dark. What is time? What is information? What is existence when stripped of form and function? The information paradox, in particular, continues to haunt physicists like a ghost at the edge of every equation. If matter and energy fall into a black hole, what happens to the information encoded in their quantum states? Hawking's initial proposal, that information is irretrievably lost, seemed to violate one of the most sacred laws of quantum mechanics, that information must be conserved. This led to decades of debate, disagreement, and refinement, culminating in various models suggesting that information may, in fact, be encoded in subtle fluctuations at the event horizon, or perhaps stored holographically in ways we barely understand. Enter the holographic principle, a radical notion proposing that everything within a volume of space can be described by information stored on its boundary. This idea, emerging from string theory and fueled by black hole thermodynamics, suggests that our three-dimensional reality might itself be a projection from a more fundamental two-dimensional surface, a cosmic hologram. This isn't just theoretical flourish, it's a mathematically consistent framework that has opened entirely new avenues of thought. Black holes, with their measurable entropy proportional to the area of their event horizons rather than their volume, seem to embody this principle perfectly. What this means, if proven true, is staggering. It implies that space and perhaps even time are not fundamental, but emergent properties of a deeper informational layer of reality. We would no longer think of ourselves as beings moving through space-time, but rather as configurations of information manifested within it. Consciousness itself might be an emergent property of information dynamics, riding waves that began long before we had names for them. And black holes, these dense, silent fonts of entropy, may be the keys to unlocking this secret architecture. But for all the speculative wonder, black holes also offer a chilling precision. They are the most efficient destroyers of order in the known universe. Drop a teaspoon of matter into one, and its mass vanishes, absorbed seamlessly into the totality. No residue, no echo, just a faint increase in entropy, an imperceptible ripple in the cosmic accounting of energy and time. And yet, even here, even in the presence of such finality, we are beginning to suspect there is more. That black holes do not destroy information, but rather encode it, somehow, somewhere, possibly smeared along the horizon in complex, quantum gravitational structures we have yet to comprehend. This is why black holes remain central to the search for a theory of everything, a unified framework that merges general relativity, which governs the cosmic and massive, with quantum mechanics, which rules the microscopic and subtle. It is in the event horizon of a black hole, at the intersection of gravity and information, that these two great theories clash the loudest and reveal their limitations. To resolve that tension is not just to understand black holes, it is to understand everything. Consider the thought experiments that continue to stretch our imagination. The black hole firewall paradox, for instance, posits that the smooth event horizon predicted by general relativity might actually be a searing wall of energy, incinerating anything that falls in, an idea proposed to resolve the information paradox, but one that breaks the very notion of what spacetime is. Or consider the ER equals EPR conjecture, which proposes that quantum entanglement, Einstein-Podolsky-Rosen pairs, is actually the same as wormhole connections, Einstein-Rosen bridges, that every entangled particle is connected by a non-traversable wormhole. If true, this would unify space-time geometry with quantum information, and imply that the very fabric of the universe is a vast web of entanglement. These aren't just abstract debates. They are the new frontiers of human understanding. They are where physics becomes metaphysics, where science becomes philosophy, where the boundary between what is known and what is imagined dissolves into a new realm of inquiry. And all of it, is because of black holes. No other object in the cosmos compels us to rethink so many aspects of our reality. Not just mass and time, but entropy, causality, determinism, and even the arrow of time itself. Black holes, in their formation, mimic the origins of the universe, a singularity giving rise to space-time. In their potential evaporation, they mimic its death, a slow dissipation into darkness. They are both alpha and omega, both the furnace and the grave of physical law. It's no wonder then that black holes are not only studied by scientists, but revered by thinkers and dreamers alike. Writers, artists, mystics, and mathematicians have all gazed into the idea of the black hole and seen a reflection of their own deepest truths. The abyss isn't just out there, it's inside us, too. The unknown. The silent center around which we orbit, afraid and fascinated. But perhaps what makes black holes most extraordinary isn't what they are, but what they make possible. Without them, we might never discover the limits of physics. Without their paradoxes, we might never be forced to unify the quantum and the cosmic. Without their pull, both gravitational and intellectual, we might never venture so far from the shores of certainty. They are the ultimate unknowns. And in chasing them, we are becoming something more than we were. And in this endless pursuit of the unknowable, something remarkable happens. We begin to redefine the boundaries of our own consciousness. Each new revelation about black holes isn't just a scientific achievement, it's a recalibration of the human narrative. With every discovery, we're not just unlocking the secrets of distant stars or colliding galaxies. We're peeling back layers of the mind, challenging the limitations of imagination, courage, and curiosity itself. There's a kind of poetic symmetry in how black holes, which devour everything, paradoxically give rise to more knowledge than any other object in the cosmos. They do not emit light, yet they illuminate. They are shrouded in darkness, yet they guide our way forward. Like mythological symbols of death and rebirth, they seem to exist at the boundary between annihilation and transcendence. In seeking to understand them, we are slowly learning to embrace the idea that destruction is not the opposite of creation, but part of the same eternal cycle. This cycle can be seen in how stars are born, live, and die. A massive star burns through its nuclear fuel, fusing hydrogen into helium and heavier elements. For millions or billions of years, it shines with fierce brilliance. But eventually, gravity wins. The outward pressure from fusion fades, and the star collapses. If the star is massive enough, not even the degeneracy pressure of neutrons can halt the implosion. It crushes itself into a singularity, wrapping itself in a veil of darkness. But what emerges from this death is not nothing. A black hole is born, a new structure, a new force in the universe. And it begins to shape the cosmos around it in powerful, subtle, and often invisible ways. It distorts the orbits of stars, sculpts galaxies, ignites quasars, and maybe even spawns new universes. We once feared the black hole as a cosmic monster, a place where all things go to die. But now we are beginning to understand it as something far more complex, perhaps even sacred. It is a crucible, a gate, a library written in the language of entropy and curvature. And it may very well be the missing link in our quest to understand the nature of existence. Let us now return to one of the most mysterious aspects of black holes: time. Einstein showed us that time is not a constant. It bends, warps, and stretches under the influence of gravity. Near a black hole, this effect becomes extreme. To an outside observer, time for an object falling toward a black hole slows down drastically. In fact, from our perspective, that object never quite crosses the event horizon. It asymptotically approaches it, frozen in time, bathed in redshift, dimming forever. But for the object itself, for an astronaut falling past the point of no return, time continues normally. They would plunge inward, experiencing the final seconds of their life as they approach the singularity. What would they see? What would they feel? The laws of physics cannot answer that question with certainty. Our equations break down. The very idea of inside the black hole becomes suspect, as does the concept of time itself. This raises profound philosophical questions. Is the future already written within the geometry of the black hole? Is every event that occurs within it predetermined, encoded on the event horizon like data on a disk? Is information truly lost, or merely transformed in ways we cannot yet decode? Some physicists now believe in a principle called black hole complementarity, which suggests that no single observer can ever witness both the outside and inside of a black hole. To an outside observer, information is smeared on the horizon, never quite entering. To the infalling observer, the information falls in normally, only to be destroyed, or transformed, at the singularity. Both perspectives are valid, even though they appear contradictory. It's a new kind of paradox, one that forces us to question the limits of observation and reality itself. And then, there is the strange and beautiful possibility of white holes. White holes are the theoretical opposites of black holes, objects that cannot be entered from the outside, but which constantly spew out matter and energy. According to general relativity, white holes are mathematical solutions just like black holes, though no physical evidence of one has ever been found. Some speculate that white holes may be connected to black holes via wormholes, forming Einstein-Rosen bridges. Others believe they may represent the rebirth of information or even new universes emerging from black holes in our own. Could a white hole be what we see when a black hole evaporates completely? Could it be the rebirth of matter and structure from pure entropy? Could the information stored in a black hole be released back into the universe at the end of its life? These are not questions for science fiction alone. They are at the frontier of theoretical physics. And what if black holes themselves are not as silent as we once thought? Recent studies of gravitational wave echoes, subtle ripples in the fabric of spacetime, suggest that black holes may not settle into perfect silence after collisions, as we long believed. These echoes could be signs of quantum effects at the event horizon, or even of entirely new physics, what some call soft hair or fuzzballs, replacing the traditional singularity with a more complex quantum structure. If verified, this would fundamentally change our understanding of what black holes are. Even more provocatively, some theories suggest that we are already inside a black hole, that our entire universe exists within the event horizon of a vast, higher-dimensional black hole in another universe. While highly speculative, this black hole cosmology idea isn't completely outside the bounds of general relativity. It's a reminder that our intuitions, built on everyday experience, may fail completely when confronted with the architecture of reality. And speaking of architecture, consider this: if we ever learn to manipulate spacetime, to control the quantum structure of gravity, could we build artificial black holes? Could we create gravitational engines for starships, time machines, or computational devices that make today's supercomputers look like stone tablets? Could black holes become tools rather than terrors? Some physicists believe they already are, at least in theory. The black hole computer is a proposed idea in which information processing occurs at the maximum possible density, governed by the laws of quantum gravity and thermodynamics. Such a machine would represent the ultimate limit of computation, approaching the bounds of what the universe allows. And according to the Margulis-Levitin theorem and Landauer's principle, a black hole could perform more operations per second per unit of energy than anything else in existence. This raises unsettling questions. If black holes are nature's perfect information processors, could they be thinking? Not in the way we understand consciousness, of course, but as self-regulating systems of entropy and information flow? Could the universe itself be a kind of vast, emergent computation, an algorithm written in the language of geometry and probability? We don't know. But we are getting closer. And closer still we draw, not just to understanding black holes, but to confronting the possibility that the universe itself operates as a conscious or at least self-aware entity, one that uses black holes as nodes of memory, as storage banks for the fundamental bits of its own existence. If every black hole is an information processor, and if every interaction with them involves the transformation and encoding of data, then we may be living in a universe that does more than expand, it computes. The implication of such a perspective is both staggering and transformative. It forces us to reevaluate what intelligence is, what awareness means, and whether our own consciousness is not a fluke of biology, but a pattern echoing something deeper. Perhaps we are not merely observers of the universe, but expressions of it, rising like waves from the quantum foam, destined to return, eventually, to that silent, churning sea of information at the edge of every event horizon. This idea finds an unexpected ally in loop quantum gravity, one of the primary contenders for a theory of quantum gravity. In this model, space itself is quantized, made up of tiny loops of spacetime geometry. These loops define areas and volumes, creating a discrete structure of reality at the smallest scales. When applied to black holes, loop quantum gravity suggests that the singularity may not exist in the way we imagine. Instead, the collapsing core of a dying star could bounce back in a kind of quantum rebound, possibly giving birth to a new region of spacetime, a baby universe. This quantum bounce, if true, would preserve information and prevent the infinite density predicted by classical general relativity. It would also mean that our own universe could be the interior of a black hole born in a higher dimensional parent universe. That's not metaphor, that's math. It's a legitimate scientific hypothesis being explored in papers and simulations across the globe. In this view, every black hole is a womb of creation, not a tomb of destruction. We are no longer talking about black holes as endpoints. We are talking about them as portals, as cradles, as machines of cosmic recursion. And if that doesn't inspire awe, consider this: the observable universe itself behaves strikingly like the interior of a black hole. It has a boundary, the cosmological horizon, beyond which information cannot reach us due to the expansion of space. The energy density, the thermodynamic properties, and the entropy of the universe all align eerily with what we'd expect if we were trapped inside an unimaginably large black hole. Could this be coincidence? Perhaps. But the deeper we dig, the more coincidences begin to look like clues. Clues to a reality that is stranger than any science fiction. It is in this spirit of cosmic humility and curiosity that physicists like Roger Penrose, Juan Maldacena, Kip Thorne, and countless others continue to probe the edges of the unknowable. With every observation, every new gravitational wave detected, every high-energy collision studied in the Large Hadron Collider, we inch closer to unveiling the complete story of black holes. Yet despite these advancements, the human mind may be the most remarkable tool we have in this quest. Because even with all our telescopes and detectors, even with satellites orbiting distant worlds, the most powerful engine of exploration remains the imagination. It was through imagination that Einstein bent space and time. It was through imagination that Hawking saw radiation where others saw silence. And it is through imagination that we now begin to consider what it means to build civilizations not around stars, but around black holes. Yes, black holes may one day become the engines of future technology. Science fiction often imagines interstellar civilizations drawing energy from stars, constructing massive Dyson spheres to harness the output of a sun. But stars, for all their beauty, are inefficient. A black hole can, under the right conditions, convert mass into energy at far greater efficiencies, up to 42% via accretion disks, compared to the sun's 0.7% through fusion. Imagine a Type 2 or Type 3 Kardashev civilization, a species so advanced that they build machines around spinning black holes, extracting rotational energy through the Penrose process or Blandford-Znajek mechanism. They could use magnetic fields and plasma jets to tap into these powerhouses and use them as interstellar batteries, fueling cosmic megastructures and perhaps even manipulating space-time itself for travel, computation, or time manipulation. Such concepts, while distant and exotic, are rooted in known physics. They aren't fantasies, they are projections. They remind us that black holes are not just exotic endpoints of stellar collapse but represent a kind of ultimate potential. They are laboratories of time, machines of gravity, and engines of transformation. And so we look up. We stare into the heavens not just with instruments but with intent, with longing, with the haunting awareness that what we are discovering out there might be a reflection of something embedded deep within our own being. For black holes are not just cosmic phenomena. They are metaphors. They are spiritual symbols. They are questions. What lies beyond the event horizon? What is the nature of the singularity? Is there something after the end? And perhaps the most important question of all, why do we care? The answer may lie not in physics, but in the poetic fact that curiosity is the signature of life. That to ask what exists inside a black hole is to proclaim that we are not content with limits. That we dare to seek answers even when we know those answers may never come. That the universe may be cold, indifferent, and dark, but within it, there exists at least one species who sees beauty in the void. A species that, despite its flaws, reaches toward the stars with trembling hands and stubborn hearts. We are that species. And black holes are our challenge. Our mirror. Our final frontier. And if black holes are our final frontier, then they are also our truest test, not just of intellect, but of imagination, endurance, and the very essence of what it means to be conscious beings navigating an incomprehensibly vast reality. In grappling with black holes, we are not simply solving equations. We are wrestling with the paradoxes of being. Because somewhere between the gravitational collapse of a dying star and the information patterns dancing on an event horizon lies the story of us. This story isn't linear. It's recursive, looping like the very space-time that bends around a black hole. As we try to understand them, they force us to reinterpret our understanding of time itself, not as a constant, but as a fluid, malleable dimension. Time doesn't just pass near a black hole, it distorts, stretches, and, in a sense, recoils. The deeper you fall into gravity's grip, the slower time moves from the perspective of the outside observer. For you, as the falling traveler, time ticks normally. For the outside world, you are frozen in place, a ghost fading toward the horizon. This concept, rooted in Einstein's general relativity, is not just theory, it's observable. We've seen the redshift of light emitted near black holes, proof that time is grinding to a halt from our vantage point. But this isn't just a curiosity, it's a gateway to entirely new understandings of causality. What if time isn't one continuous thread, but a patchwork of perspectives, stitched together by gravity? What if black holes aren't just objects, but intersections, places where different timelines meet and diverge? This leads us to yet another captivating notion, the possibility that black holes are gateways not just to other places, but to other nows. To different eras, to alternate histories or futures. Though this borders on science fiction, there are models within theoretical physics, specifically those involving wormholes or Einstein-Rosen bridges, that suggest such passages could, under highly specific and controlled conditions, allow for temporal dislocation. While we've yet to discover practical ways to stabilize such a passage, the very fact that mathematics doesn't outright forbid it is both thrilling and humbling. And consider this. What if time itself emerged from the thermodynamic processes inside black holes? Some theories propose that time is not a fundamental feature of the universe, but a macroscopic illusion born of entropy. Black holes, as entropy monsters, could be responsible not only for shaping the cosmos gravitationally, but causally. If time is born from entropy, and entropy finds its most intense expression in black holes, then perhaps these dark giants don't just mark the end of time, they may define it. This opens the door to the radical possibility that the past, present, and future are all encoded in the structure of space-time, much like grooves on a vinyl record. And black holes may be the stylus that reads, writes, or erases that cosmic record. Could they be the arbiters of destiny itself? Could the birth and death of stars, the dance of galaxies, even the rise of consciousness, be written into the gravitational field of the universe, with black holes as the punctuation marks? And what about life? Could black holes play a role in the evolution of consciousness? Some scientists have speculated about the anthropic implications of black holes, that is, the idea that the universe is fine-tuned for life because only a universe with certain conditions would allow observers like us to exist. Black holes might be a part of this fine-tuning. Without them, galaxies might not form as they do. Supermassive black holes anchor galaxies, influencing the formation of stars and planetary systems. In a very real way, black holes may have sculpted the conditions necessary for life to evolve, quietly shaping the stage long before the actors emerged. But the idea goes deeper. Physicist Lee Smolin proposed a controversial hypothesis called cosmological natural selection, in which universes reproduce through black holes. In this model, each black hole gives birth to a new universe with slightly varied physical constants. Universes that produce more black holes have more offspring, making black hole production a kind of evolutionary advantage in the multiverse. Over countless generations, universes evolve that are optimized for black hole formation, our universe being one of them. If this is true, then black holes aren't just endpoints, they are wombs. They are the reproductive organs of the multiverse, And we, as a byproduct of a black hole-rich universe, may owe our very existence to the evolutionary pressures exerted by cosmic reproduction. The universe, then, becomes not a static expanse, but a living, self-replicating entity, a cosmic organism, with black holes as its genetic engines. This theory remains speculative, but it's emblematic of something profound. Black holes refuse to be pigeonholed. They are not merely physical objects, but metaphysical provocateurs. They challenge every category we try to place them in. They are simultaneously the simplest and the most complex structures in the universe. They are defined by a few basic parameters: mass, charge, and spin, but beneath that apparent simplicity lies a kaleidoscope of paradoxes, puzzles, and potentialities. Take the no-hair theorem, which asserts that black holes are bald, meaning they contain no details about the matter that formed them beyond mass, spin, and charge. Two black holes of equal mass, spin, and charge are indistinguishable, even if one formed from collapsing stars and the other from exotic dark matter. But if information is preserved, as quantum theory insists, then where is it? How is it stored? This is the heart of the black hole information paradox, and solving it may rewrite the laws of physics. Stephen Hawking's final works leaned into this question. He proposed that information might be stored on the event horizon, preserved in a kind of holographic projection. This idea aligns with the broader holographic principle, suggesting that everything we experience in 3D could be encoded on a distant 2D boundary. In this view, the entire universe becomes a hologram, and black holes become the clearest evidence of it. If we are living in a holographic universe, if space and time are emergent properties of deeper, hidden dimensions of information, then black holes are more than cosmic curiosities. They are the smoking gun, the pixelation in the matrix, the exposed code in the simulation. They are the anomalies that hint at the grand illusion. And once again, we return to the mirror. Because in studying black holes, we are not only decoding the universe, we are decoding ourselves. We are pattern-seeking beings staring into the abyss and seeing reflections of our fears, our hopes, our yearning to matter in a universe that doesn't need us, but that we strive to understand anyway. We chase black holes because they represent the edge of physics, the edge of knowledge, the edge of what we are capable of knowing. And we chase that edge because we are built to push boundaries. We are, by our nature, explorers, not just of space, but of thought. What lies beyond the edge? That question may never be fully answered. But perhaps the point is not to know everything, but to try, to dare, to dream. And black holes, with all their darkness, paradoxes, and terrifying beauty, invite us to do exactly that. So we continue our pursuit, not because we believe we will conquer the mystery of black holes, but because the pursuit itself transforms us. Each step forward demands that we shed outdated assumptions, refine our understanding of reality, and stretch the limits of what we believe is possible. This isn't just science, it's a kind of existential pilgrimage, one that takes us into the most forbidden regions of the cosmos and forces us to reflect on the nature of everything we think we know. And yet, amidst all this theory and abstraction, black holes remain real. They are not speculative. They are not myths. We have seen them. We have detected their fingerprints in the ripples of space-time and captured their silhouettes against glowing backdrops of light. In 2019, the Event Horizon Telescope collaboration revealed the first image of a black hole's shadow, a dark void encircled by a blazing ring of superheated matter spiraling into oblivion, 55 million light-years away in the heart of galaxy M87. That image was more than a scientific achievement. It was a message from the abyss. A silent, circular echo that whispered across time and space, "I exist." In that haunting, blurry ring of fire, humanity saw proof that our wildest equations were not merely mental gymnastics, but accurate descriptions of the real universe. The image of the M87 black hole confirmed that Einstein's theories held strong even at the edge of the extreme. But it also opened new questions. Why did the shadow appear so stable? What do the properties of its spin and mass tell us about its origin? Could this data reveal deeper truths about the structure of spacetime itself? Since then, more observations have followed. We've detected black hole mergers using gravitational wave detectors like LIGO and Virgo, momentary blips in spacetime that shake our planet ever so slightly, like the faint thump of distant drums. These events are incredibly rare and brief, yet the universe is full of them. It turns out that black holes are not rare cosmic oddities, they're common. And they come in a wide range of sizes and behaviors. Some black holes are stellar mass, formed from the collapse of single massive stars. Others are intermediate mass, still poorly understood but existing in the thousands or tens of thousands of solar masses, possibly the missing link between stellar and supermassive black holes. Then there are the behemoths, millions or even billions of times more massive than our Sun, sitting at the hearts of nearly every galaxy, including our own Milky Way. The black hole at our galactic center, Sagittarius A, is 4 million times the mass of the Sun, and its gravity commands the orbits of stars like a conductor with a silent baton. But even as we catalogue and observe, we remain haunted by anomalies. There are black holes that spin faster than our models predicted. There are gravitational wave signatures that hint at unexpected asymmetries. There are whispers of primordial black holes, tiny, ancient remnants from the earliest fractions of a second after the Big Bang, hiding in the vastness of space, potentially contributing to the dark matter that makes up most of the universe's mass. Yes, dark matter, yet another of the cosmos's enigmas. We know it's there because galaxies rotate too fast to be held together by visible matter alone. Something unseen provides the glue. Could primordial black holes be part of that glue? Could black holes be hiding within the invisible scaffolding of the cosmos? Some theorists suggest so. If black holes formed in the early universe from fluctuations in density, they could be floating through the universe right now, undetectable unless they pass in front of a star and lens its light, or collide with something detectable. These black holes wouldn't be created by dying stars. They'd be older than stars, relics of a pre-stellar epoch. They might not even have horizons in the traditional sense. They might represent something even more bizarre, objects that never became true black holes, but sit on the edge of possibility, teasing us with almost horizons. And if this is the case, then black holes may not just be endpoints in cosmic evolution, they may also be beginnings. Primordial seeds from which galaxies grow, or even space-time itself blossoms. But let us not forget the personal aspect of black holes, the human story. For centuries, the idea of an object so dense that not even light could escape seemed absurd. John Michell, a geologist and clergyman, proposed the concept in 1784, calling them dark stars. Later, Laplace echoed the idea, but the notion was dropped until Einstein's general relativity revived it. Even then, Einstein himself doubted such objects could physically exist. They seemed like mathematical artifacts. It wasn't until the work of scientists like Carl Schwarzschild, Robert Oppenheimer, Subrahmanyan Chandrasekhar, and Roger Penrose that black holes took center stage in astrophysics. And it wasn't until Stephen Hawking entered the picture that they took on their paradoxical glow. Black holes, the ultimate absorbers, emitting radiation. His theory of Hawking radiation turned everything on its head. Suddenly, black holes were no longer eternal. They could evaporate. This changed everything. Now black holes had lifespans. They were born, they consumed, they aged, and they died. The ultimate cosmic predators, brought low by quantum effects at the horizon. But Hawking's theory also introduced the deepest mystery of all, the information paradox. If black holes evaporate, and information cannot be destroyed, where does the information go? This single question has inspired entire generations of physicists, who have followed the threads of string theory, holography, quantum gravity, and firewalls in their quest for an answer. The stakes are no less than the unity of the two greatest theories in science, general relativity and quantum mechanics. And in the end, maybe it's not about one winning over the other. Maybe the answer lies in their marriage, a new synthesis, as yet unnamed, that will bridge the smooth curves of spacetime with the probabilistic jitters of quantum fields. Black holes will guide us to that synthesis. They are the crucible in which old ideas are melted down, and new ones forged. They are where physics grows up. And still, despite all our progress, we are left with mystery. The center of a black hole, the singularity, remains veiled. Not just by the event horizon, but by our own ignorance. It is a place where density and curvature become infinite, where our equations yield infinities and our theories fall silent. Maybe the singularity is not a place, but a boundary, a sign that our current understanding is incomplete. Maybe it is not a thing, but a question: what lies beyond? And so we keep asking. We look deeper. We build better instruments. We refine our theories. We simulate, calculate, dream. We send our minds where our bodies cannot yet follow. Because black holes are not just cosmic destinations. They are our destination, as thinkers, as explorers, as beings defined by our desire to understand. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.